Welcome students to our new lesson. In this lesson, we'll discuss position of secondary minima and your intensity distribution curve. So in our last class, we have derived the expression for your path difference. The light, the extra path the light has to follow this path, Bn. This is your extra path difference. This extra path difference is given as d sine theta. D is the distance between the slits and theta is the angle by which it is diffracted. It is moved from the original. Fine. This is your central one. Okay. And by how much angle it has been elevated? This is your diffraction angle theta. So your path difference P equals to D times sine theta. After this, we have derived the expression for the position of minima. That means at what points on the screen we will get dark fringes. So the position of minima is given as theta equals to n lambda by t. This theta shows us at what angle. So in our case, we will assume this angle as our position. So at what positions you will get a dark fringe, your minima or your minimum intensity. So whenever your diffracted angle theta, this is a multiple of n times lambda d upon d. N is your integer number. It can be 1, can be 2, can be 3, and so on. Lambda is your wavelength, the wavelength of the light used. And small d is the distance between the slit. The size of the slit is small d. So whenever your theta, the position of the dark fringe or the angle of the diffraction angle for the dark fringe will be given as n lambda upon d. Fine. The condition was that the path difference should be a integral multiple of lambda. Fine. The path difference should be multiple of lambda. If there is a complete wavelength distance between this path difference, only then you will get a dark fringe. Right? So in our today's class, we'll derive the position of secondary maxima. Fine. Why secondary maxima? Because we know at the center we will obtain your central bright fringe. And why is it so? Because at this center, consider this ray AO, consider this ray BO. All of this light falls on the screen with no nil path difference. Okay, there is no path difference between this light and there is no path difference between this light, and so on. Fine. If there is no path difference, in that case, all of the light falls on this point O without any phase difference. In that case, you will get a central bright fringe. So after central bright fringe, the next bright spot which you'll obtain on the screen will be known as your secondary maxima. Now let us consider your light is diffracted at such an angle. For our simplicity, okay, let us consider this one as theta 1. But since this is for your secondary maxima, let's put a dash here, okay, to avoid confusion, okay. For minima, I'll just use theta 1. But for maxima, let us use theta 1 dash. Fine. So let us suppose your lights are diffracted at this angle, theta 1 dash. So what happens when the light is diffracted theta 1 dash? The path difference is thrice of lambda by 2. Fine. Look here. This is lambda and this is thrice of lambda by 2. Okay. Up till this point, this is how much? Lambda. Fine. Up till this point is your lambda and this is half of your wavelength. That means lambda by 2. Fine. So how much is lambda plus lambda by 2? Add it yourself and check. It comes thrice of lambda by 2. Fine. So when your light is diffracted such that the path difference is thrice of lambda by 2. Okay. In that case, okay, what we can do is we can divide this number of slits. Okay. Divide this number of slits into 3 equal halves. 0 to 4 in your first part, 4 to 8 in your second part, 8 to 12 in your third part. So we have divided the slits into 3 equal parts and each part consists of 4 different slits. Fine. So now look here. So now why we have divided into 3 equal halves? So that the part difference at this point becomes 3 lambda by 2. The part difference at this point becomes lambda and the part difference at this point becomes lambda by 2. Fine. Okay. Now, just like I have explained in my previous class, okay, what happens is that consider the light coming from this point 0 and consider the light coming from this point 4. Okay, now the light coming from point 0 has to travel this much distance, whereas the light coming from this point 4 has to travel an extra distance. This distance is equivalent to lambda by 2. Fine. If this extra distance travel is equal to lambda by 2, then in that case, what will be the phase difference? If you remember, this was the expression for the phase difference. And if the path difference is lambda by 2, substitute lambda by 2 here. Then in that case, what happens? Lambda gets cancelled. 2 and 2 gets cancelled. So how much is your phase difference? Pi. So what happens when a phase difference is of pi? Okay, so consider this is the light coming from the point 0. This is the light coming from the point 0. And this is your another light which is coming from your point 4. Okay. Now the light coming from the point 4 has a phase difference of how much? Just now we have calculated the phase difference of pi. Fine, so let me introduce. So if you check out here, okay, this represents the light coming from the 0. This represents the light coming from 4th point. Okay, now can you see I've introduced a phase difference of how much? Pi. Now if you see what happens if there is a phase difference of pi, if I bring it together, okay, now in this case what happens? See, the crest of the second wave and the trough of the first wave, they both interfere. This has a magnitude of how much? 1. This has a magnitude -1. So both of this will interfere constructively or destructively. They will interfere destructively. So you'll get this green wave. That means what is the amplitude? The amplitude is 0. Can you see? At whatever point the magnitude is 0. So that means the two waves cancel each other, right? Okay, this was for the light coming from the point 0 and the light coming from the point 4. Okay, so the light coming from 0 and the light coming from 4 cancel each other. But what about the light coming from the point 8? The light coming from the point 8 will go and interfere. Okay, this will go and it will strike the screen. Since no one is to interfere with this light, therefore it will go and strike at the screen at this point P to produce a bright fringe. Fine. Fine. So now consider the light coming from the third point. Okay. Okay. If the light is coming from a lambda, okay, what will be the phase difference? Do they follow the same step? The phase difference will be twice pi lambda times P. Fine. Now in this case, how much is the path difference? Lambda. So substitute lambda out here. So if you substitute lambda, this one and this one gets cancelled. And how much is the phase difference? 2 pi. Okay. By the way, since the light coming from this point 0 is being cancelled by the light coming from the point 4. But for the light coming from this third part, okay, the light coming from this third half, the light coming from this point 8, is there any other part to cancel this point 8? No. So in such case, we don't require this phase difference also. Okay, doesn't matter whatever be the phase difference. Okay, doesn't matter whatever be the phase difference. Anyway, it will go and it will strike on the screen at this point P to produce a bright fringe. Fine. So now look here. Now you have a third wave coming into a picture. Fine. This is your third wave. When the third wave comes into the picture, what happens? The red wave and the blue waves cancel each other. But what will happen since the third wave is striking on the screen? Therefore, you'll get a resultant wave. And why is this resultant wave coming? This is only because of the third wave. The red wave and the blue wave. Again, I'm telling this red and the blue wave are cancelling each other. The only contribution is coming from the third part. Fine. This is how it looks. Okay. So what will happen? The light coming from the third part will go and strike on the screen and you will get a bright fringe. Fine. So this at the screen, this will be called as your secondary maxima. So the condition for the first secondary maxima will be this one. That means the path difference equals to 3 lambda upon 2. You know what is the path difference expression? It is d sine theta. So let us substitute the value here. I can write d sine theta, but will it be theta? No. At what angle we are getting? Theta 1 dash. Fine. So this will be d sine theta 1 dash equals to thrice of lambda by 2. Fine. If you follow the similar pattern, okay, you consider another point on the screen, further away from the screen. That will be your second secondary maxima. So the condition for the second secondary maxima, I'll just directly write down the second secondary maxima. Okay, it will be simply add 1 here. So this one will be, if it's 3 lambda by 2, this one will be 5 lambda by 2. And so this is your condition for the secondary maxima. Okay, so from here, what you can derive? Just look at this pattern and tell me what will be the condition for the nth secondary maximum. So for the nth secondary maximum, okay, first let us look. This d will remain same. Okay, but look at this angle. For first, it was theta 1 dash. For second, it is theta 2 dash. So for the nth secondary, it will be theta n dash. Fine. Similarly, look here. what you observe this one, this is 3 lambda by 2, this is 5 lambda by 2, the next one will be 7 lambda by 2, the next one will be 9 lambda by 2. So what you observe is that all of these are in odd multiple of lambda by 2. Can you see? Lambda by 2 multiplied by 3, lambda by 2 multiplied by 5. So 3 and 5 are your odd numbers. So I can write d sine theta n equals to odd number times lambda by 2. And how did we wrote our odd numbers? Let's put a bracket first. So 2n, okay, this is your even number. 2n is your even number. And if I add 1 here, then it will become a odd number. Fine. So 2n plus 1 is a odd number multiplied by lambda by 2. Fine. Fine. So this is the condition for the secondary maxima. Okay. Next, what we will do, we will find out the position. To position, we have to find this angle. Okay, so to find out this angle, what we can do is, let us make an assumption. The assumption is that this angle is very, very small. If this angle is very small, then I can write sine theta n dash as theta n dash. Right? Fine. So using this assumption, I can write this expression as d theta n dash equals to twice of n plus 1 lambda by 2. Now send this d to the denominator. Fine. So theta n dash equals to twice of n plus 1 lambda upon 2t. So this is important as this is the position. At what angle I'll get your secondary maxima can be determined by this angle. Fine. So I have derived the expression for the path difference. And then we have derived the condition for the nth dark fringe, the position of the nth dark fringe or the position of minima. Then we have derived the condition for the secondary maxima, the position for the secondary maxima. Fine. Now moving on. Next, we will show graphically the variation of intensity with angle in the diffraction pattern. If we change this angle, how my intensity changes. Okay, for intensity distribution, consider this part, the part from the lens to here. Okay, now let us consider for your central maxima. For your central maxima, consider the light coming from the point 0. This is the light coming from here. This is point 0. Fine. Or let us say the light coming from one corner. Consider the light coming from the center. The light coming from this point C. Similarly, consider the light coming from point B. From this point. I am talking about this first ray, this second ray, this third ray. Okay, I'm showing the picture of only this part, the one which is focused after the lens. Okay. So in this case, all of the three waves are in phase with each other. Therefore, you'll get a resultant wave. This is a bright spot on the screen. Fine. Now, after your central maxima, come to your first dark fringe. Fine. For your first dark fringe, what we did, we considered the slit, we divided into two halves. So consider the light coming from this point 0 and consider the light coming from this point 6. So the light coming from this point 0 and the light coming from point 6. Since these two waves are out of phase with each other, what will happen? The two waves will cancel each other and on the screen you will get a dark fringe. Fine. Now coming to our maxima. Now for this maxima, we have divided the slits into three halves. Consider the light coming from point 0, consider the light coming from point 4, and consider the light coming from point 8. This is the light coming from point 0. This is the light coming from point 4. Now consider the light which comes from the point 8. Now what happens? The light coming from this point, your 0, okay, and the light coming from the point 4, these two light cancelled each other. Okay, these two lights are out of phase and they cancel each other, just like in your dark fringe. Just like your dark fringe, the two light waves also cancel each other, but the light coming from the point 6 will contribute to the interference. Can you see the green wave? This will contribute to give a bright spot. Fine. So out of this two, only the third part is giving contribution. Therefore, you see a light. But tell me, what is the difference you notice between the first bright spot and your second bright spot? Okay, let me just remove this dark fringe, okay, for simplicity. Fine. To avoid the confusion, now look here. For the central bright fringe, what you notice is that all of the waves contribute. The first wave, the second wave, as well as the third wave. They contribute to give a resultant intensity. But in this case, the first wave is being cancelled by your second wave. The only contribution comes from the third part. So can you see the intensity? The intensity has reduced. First, this was your intensity somewhere around very high 6, but now the intensity has reduced to how much? Okay, just look at this part, this magnitude part. If you want to compare the magnitude of this two, let me bring this intensity down. Look, this is the intensity of the central bright fringe, and this is the first secondary maxima. Can you see that gap in the intensity? In this case it is 6, in this case it is 2. Fine. So from here what you notice is that the intensity has reduced. Fine, the intensity has reduced for the first secondary maxima. Similarly, the intensity will keep on reducing as we go forward. Okay, so if I have to draw the intensity curve, this is how it will look. For the central bright fringe, you have the highest intensity. But as you go forward, since the contribution part becomes less, only the third part is contributing, so intensity decreases. In this case, only the fifth part will contribute, intensity further decreases, and so on. Fine, so the intensity keeps on decreasing. Similarly, the same pattern will be followed on the other side. So this is the intensity variation for the diffraction pattern. Fine. From the board perspective view, okay, from the board exams, you have to only remember this equation. What is the path difference? Path difference equals to d sine theta. No need to remember this derivation and the diagram. Just remember the path difference equation. Similarly, here you just have to remember the condition for the nth dark fringe and the position of the nth dark fringe. Just this two equation. No need to remember this derivation part. Okay. Similarly, in this secondary maxima, no need to remember the derivation part. The only important part is this condition for the secondary maxima and the angle, your position for the secondary maxima. No need for this diagram also, fine, because this questions comes directly as an objective. Okay, they simply ask for 1 marks or 2 marks. There you can simply directly write down these values and you'll get marks, right? So, and also remember this intensity graph. Okay, they ask you to draw the intensity variation. So that's it for today's class. Thank you. And if you have any confusion, please don't hesitate to ask. I'll re-explain it to you again. So again, thank you.